So first off, let's talk about drag. Drag is the force that fluid exerts on an object moving through said fluid. In this case, air is our fluid and our cars are our objects. There's a pretty straightforward equation that can be used to calculate the force of drag against an object. The force of drag is equal to the drag coefficient times the frontal area times the density of your fluid times the velocity of your object squared, all divided by 2. For the sake of our calculations, we'll assume that our cars are moving at 33.5 meters per second, or about 75 miles per hour, and the temperature is 20 degrees Celsius, or 68 degrees Fahrenheit, which means that the density of our air will be 1.204 kilograms per meter cubed. Now my truck has a drag coefficient of 0.39 and a frontal area of about 2.3 meters squared. Plugging this into our formula shows that the force of drag against the truck under the given conditions is about 606 newtons. Cohen's Camaro has a drag coefficient of 0.35 and a frontal area of around 2 meters squared. This yields a drag force of about 483 newtons. Chris's FRS has a drag coefficient of 0.27 with a frontal area of about 1.9. This gives us a drag force of about 349 newtons. Finally, our little MX-5 has a drag coefficient of 0.38 and a frontal area of about 1.6. This gives us a drag force of about 420 newtons. So looking at our results side by side, it makes a lot of sense. The truck has the highest drag force because of its size, shape, and purpose. It wasn't made for speed or fuel efficiency. Its purpose is to carry stuff from point A to point B. The Camaro has the second highest drag force. It's classified as a muscle car, so again, it wasn't designed with fuel efficiency in mind. It uses a large engine to power through the air instead of cutting through it. Next is the little MX-5 with a drag coefficient that is almost the same as the truck. However, it has a tiny frontal area, which makes up for this high CD. Finally, the FRS is sleek and small and is designed to cut through the air, hence the low drag coefficient. This is reflected in the low drag force under our given conditions for the FRS.
So, now that we've heard about drag, let's hear about the other force that acts on cars. This force is called the lift force. What happens with lift is, like drag, it is affected by the wind. So, with the drag, it pushes against the front of the car, whereas lift more pushes on the bottom of the car. Now, why does this happen? Is because when you're driving, the air going over the car has a higher pressure than the pressure under the car. So what this does is the higher pressure pushes up against the car. And that's not necessarily good for fuel economics. So, and you can see in this video, as the car speeds up, the more lift it gets, this nose goes up. And that's not necessarily a good thing when you're trying to get your wheels on the ground. Maybe for planes, but not for cars. So why does this happen? Well, if you look at the formula for lift, you can see it's very similar to the force of drag as well. So the only difference is this coefficient of lift. What's different is the coefficient of lift is normally smaller than the drag coefficient. So, and as you can see, the more velocity you have, then the more lift you'll get, which is not good, which is why as this car speeds up, its nose end goes up more.
Drag and lift are both major factors on cars' handle and maneuver through the air upon the road. There are 4 main modifications that can be done to change and affect these coefficients. They are airfoils, ducktails, splitters, and diffusers. Airfoils and ducktails are mainly for drag and downforce on the rear wheels. These cause major or slight differences in the drag coefficient depending on how aggressive of the angle that you make them. First, the airfoils or wing is normally used for high speeds and to add large amounts of downforce to the rear to help keep traction on the rear tires. This works as the air goes over the cars and hits the wing and splits. As the air splits around the wing, there is a longer path across the top, which creates higher pressure and forces the air down, creating a downforce, whereas on the lower side there's a low pressure causing the allowance for the wing to go down and not have too much resistance causing the downforce. This also works as air behind the car becomes more turbulent, reducing the vacuum out in the car, allowing it to reach higher speeds. The ducktail acts very similar to the wing, except for the fact that instead of splitting the air, it catches the air and causes a pocket of high pressure to force the rear down. The ducktail causes less downforce because it has normally a lower area that is affected by the air hitting it, causing less downforce to be applied. These are used for a more casual need or just to help with that little bit of downforce needed to drive on the highways in a lightweight car going 80. They are smaller and less noticeable than wings, and most cars that say they are performance cars have them. Splitters, or front lips, are a modification that many people dislike whenever they are on street cars, because they give it a look of lowering without actually lowering their car, or are already on lowered cars, making them look even lower. Splitters are used like ducktails, but on the bottom front lip of your car, causing the air to be caught and force the front end down, which also causes less air to go underneath your car, reducing lift and downforce towards your front end. Diffusers are the last main modification that changes lift and how the air moves around the car. Diffusers go underneath the car, and the purpose of them is to channel the air that goes underneath the car and diffuse the air and cause the lift to drastically reduce. Diffusers are good for people that are trying to reduce the amount of lift possible on their car and have too light of a car to where the lift is the biggest issue when worrying about higher speeds. Earlier, we discussed the drag force that acts on each of our cars, with the truck having the highest drag force and the FRS having the lowest drag force. This calculated force is one factor that affects fuel efficiency of cars, with the others being weight, engine side, and others. The truck has poor fuel efficiency when compared to the MX-5 or the FRS, in part due to the high drag force acting against it. This makes sense because there is a greater force opposing the motion of the car, meaning that the engine must work harder to overcome it. The MX-5, however, has a similar drag coefficient but good fuel economy due to the low frontal area causing less drag force to occur. Also, this is a perfect example showing us that the other forces are involved with the fuel consumption, since it has a similar fuel economy to the FRS, even though the drag coefficient is significantly different.